Hello and welcome. This is Dr. Schleich, and in this work example, we're taking a look at question 1 of paper 2 that was administered in the summer of 2021. And it reads, complete table 1.1 by stating whether each of the quantities is a vector or a scalar. The quantity that we want to consider first is acceleration. Acceleration is definitely a vector, right? There's a direction associated with the acceleration, right? And it's the rate of change of velocity. So it's good to kind of define it too. So it's a vector quantity defined as the rate of change of velocity. And it's measured in meters per second squared. Electrical resistance, so you may recall that resistance is a ratio of voltage to current. It's like how much does the piece of metal resist the flow of charge? That's just a scalar quantity. There's no direction associated with electrical resistance. But momentum is another vector quantity. Again, the momentum is defined as mass times velocity, and whatever the direction of velocity is the direction of momentum. So vectors, remember, are a quantity with both magnitude and direction, and you kind of think about each one, does it have a direction associated with it? I just mentioned a moment ago that the conditions for equilibrium are there's no net force acting on the object and there's no net torque. You could word that different ways. The sum of the forces is 0. The sum of the torques, about any point, or the moment of force about any point is 0, but no net force, no net torque is a nice, concise way of thinking about it. An object is in equilibrium if there's no net force and no net torque acting. So that's part B. We're probably going to need to consider the conditions of equilibrium with this one here. So part C, there's a nice figure 1.1 there, not to scale. And oftentimes they include the information on the figure that they then sort of state in the paragraph. And so let's see if we got all this information here. A floating solid cylinder is attached by a wire to the seabed as shown in figure 1.1. All right, so they've got the weight of the cylinder is given, the cross-sectional area of the cylinder. They've labeled here the surface of the water. There's a depth from like the surface to the bottom of the cylinder that's given 19 centimeters. The water density is given 1,000 kilograms per cubic meter. And in fact, the first definition of the kilogram had to do with sort of the mass of an amount of water, and that's why it's such a nice round number for the density of water. The kilogram was initially defined that way, as a certain amount of water. It's defined differently now, but that's why. All right, and then the seabed, and it's not to scale here. You could imagine that, there's a lot of distance from here to the bottom of the sea, but this is only 19 centimeters here, so not to scale. It's a very shallow, part of the ocean. The wire and the central axis of the cylinder are both vertical. The cylinder is in equilibrium, right? So the conditions for equilibrium, no net force, no net torque. It's not really a torque kind of problem, right? Like there's no sensible pivot, taking moments about. So we're probably just going to need to consider that there's no net force acting on that cylinder with whatever we're going to do with it. Let's see what that is. So the first thing is calculate to 3 significant figures the upthrust acting on the cylinder due to the water. Okay, so that's one thing. And then we want to show that the tension T in the wire is 15 newtons. All right. And then it says that the wire has a cross-sectional area and it's given in square millimeters. I want to calculate the stress in the wire, right? And the surface of the water gradually rises until it is level with the top face of the cylinder. State and explain qualitatively the variation of the strain energy stored in the wire as the water surface rises. Okay, I kind of want to put that one out of my mind for right now, and we'll deal with that when we get there. Let's sort of do all these calculations that we need to do. So right away, by previewing the question, you kind of get a clue as to the physics that's going on here. There is a difference in pressure, the further down that you sort of go in the water. So these are sort of chapter 7, matter and materials ideas, right? Density is a sort of materials idea. And so some of those ideas we want to kind of keep in mind. There is some dynamics concepts at work here with equilibrium, right? For the object to be in equilibrium. So they give us the weight, right? And let's kind of remember that weight acts straight down. If that were the only force, this thing would sink. Okay. So it's suggested in the question, they say calculate to 3 significant figures. There's an upthrust force here, right? So there's a force from sort of the difference in the pressure of the water that's pushing up on this thing, right? So there's going to be more sort of pressure down here, and so there's a force that's sort of pushing up. Now there's also forces sort of pushing on the sides of this, but they're sort of in balance. And so the left's equal to rights. There's no net force in that direction. There's a weight of the cylinder, but the upthrust is obviously supplying, enough force to keep this thing floating. And they say that there's also tension T in this, string. So there's a force of tension in this string here. And so what direction is that going to act in? Well, that's got to be sort of holding it down, right? It's holding it in place. So we'd expect that when we calculate the upthrust, it's going to be greater than 28. Okay, I imagine that there's a path to calculate the upthrust based on some other physics. And again, it's like a chapter 7 kind of an idea. So in chapter 7, we talked about density. And we said, well, we could use the definition of density. We talked about pressure. And we said we can use sort of the definitions of pressure. And we'll save that, reminder for another video. But density is mass per volume, and pressure is force per area. And we kind of combine those ideas by considering sort of a block of water, and we got this equation for hydrostatic pressure. Check the link above if you wanted to see the derivation of this equation. But once we sort of have it in mind that, hey, we've got a density, we've got a difference in height here, right, from the surface of the water to the bottom of the water, we could calculate what sort of the pressure force is here. Because pressure is force per area, and we're conveniently given the cross-sectional area of this thing, we could say, well, what's the pressure down here, right? And then calculate the force, the upthrust force, which comes from that pressure, by just multiplying the pressure by the area. So we'll use this equation to solve for the pressure down here. Once we know the pressure, we can plug it in here and calculate the force that way. That force that we calculate here is the upthrust force. We can anticipate it's going to be bigger than 28. Remember, we have to calculate the tension here. Well, what's our path to doing that? There's no equation like this for tension, like, oh, the density of the rope and the length of it or something like that, right? There's just no equation like that. So the only path to get the tension is to use the ideas that we've previously been considering out of equilibrium, right? So these forces are in balance. This thing is floating there. So the weight's acting down. The tension is pulling it down because this upthrust force is the greater force that's acting up, right? The up's got to equal the downs. And so we kind of, I kind of imagine that the upthrust force over here is going to be equal to the sum of the weight and the tension. Right, so the upthrust is going to equal both of those forces. A very sort of simple way to think about it, but that's going to be the path to the solution. W plus T equals U, U for upthrust. All right, so we've kind of roadmapped our way to the solution. Now we just got to solve it. Nice. All right, so we'll solve for the pressure first. Pressure is equal to density. That's given here, and it's given in nice convenient units. And so 1,000 kilograms per cubic meter. G, we'll assume that this cylinder and this seabed is here on this planet. They don't tell us otherwise, so that's a safe assumption. And then the height here is just the difference in sort of the height from the bottom of the cylinder to the surface of the water, right? Like this is the material whose density, sort of we're plugging in here. Newtons per kilogram or meters per second squared are equivalent units for G, 0.19 meters. So we don't really have to worry about converting anything. All right. Kilograms are going to cancel. This meter is going to cancel one of those. And so the units of pressure here, we're getting newtons per meter squared. See how that's force per area? So that's kind of nice when you consider the units and you're like, all right, I'm solving for pressure, newtons per square meter. Yep, that's a force per area. And it reminds you kind of what we need to do with it next, right? Plug it in here and solve for just the newtons of force. Right? And again, we know what the meters squared of area is, right? We've already got that. All right. All right, YouTube audience, go ahead and take out your at-home calculators. If you're just like, well, I'm too lazy to get out my calculator, Dr. Schleitz. Like, oh, don't worry, I got you here with this on-screen calculator. Just pay close attention. 1,000 times 9.81 times 0.19. All right, go ahead and do it in your head, every mental math genius out there. Leave it down in the comments below. Did you say 1864? Well, you're wrong. It's 1863.9. But that's pretty close, so well done. Well, I rounded it. Yeah, but not to the correct level of significance. All right, so we'll say the pressure is 1863.9. Remember, that's newtons per meter squared. Pop quiz. What is the SI unit, derived unit, that's equivalent to a Newton per square meter? Leave it down in the comments below. Or call it out right now if you're in class. You guys know this triangle here? You guys know whose triangle this is? Pascal's triangle. So a Pascal of pressure, Pascal's triangle. Blaise Pascal, we honor him by naming the unit of pressure after. Let's get that Pascal triangle out of there. So Pascals of pressure is a Newton per square meter. All right, so now we'll go ahead and solve for the force. So that's going to look like, I'll do this working over here. Force is going to be pressure times area. The pressure we've already solved, 1863.9 newtons per meter squared. And the area, the cross-sectional area of the cylinder is, again, conveniently given right there, 0.0230 meters squared. Note how there's a 0 here at the end, and they were very specific in their instruction, calculate to 3 significant figures the upthrust. And so they're sort of reminding you with the precision of this, quantity, that that's the precision going in, that's the precision we want coming out, that's the significance we want coming out. All right, well, since we were practicing some mental math a moment ago, let's go ahead and do this one. 1863.9, not 1864 times 0.023. And so if I just kind of do that in my head, I get, well, I'll just do it to the 10,000ths place, 42.8697. Yeah, I think that's right. And so let's just call that 43. 43 newtons of upthrust. Our original hypothesis that it should be greater than the weight, holds here. The weight's given 28 newtons. And so now the tension just kind of solves itself, right? It's going to be the difference between 43 newtons and the weight 28 newtons. So you get a force of tension equal to 15 newtons, right? 15 newtons of tension holding it down, 28 newtons of weight sort of pulling it down, balances the 43 newtons of upthrust that we just solved for. And again, it's using pressure, the equation for hydrostatic pressure, and then just the general equation for pressure, which is always force per area, right? So you just have to kind of see what you're given, think your way through it. Doing more practice problems helps make the physics more familiar. So you kind of see the path to the solution and just kind of know you got your work cut out for you. Like, okay, got to plug this in, got to solve this. One calculation leads to the next step. Let's just make sure. So 42.8697. We recorded that to 3 significant digits like it asks us to. We'd say what? 42.9. 42.9 would be the best answer on this line here. And if you rounded it to 43 there, then you didn't follow directions. So always follow directions. If it says to 3 significant figures, make sure you're recording it for that level of significance. So the best answer here would be 42.9. And it says show that the tension is 15. So that's nice. When we didn't even know that, we just said, like, okay, we're going to calculate the tension, or maybe we did kind of preview it, but it leads to the answer they suggest it should be. So that builds your confidence that we're on the right track with that. This is really just using Newton's laws, right? Like something is equal. If something is in equilibrium, then the forces are balanced. And so this is just a sort of the ups equal the downs, right? The up thrust equal the down forces. So that's all forthcoming. But don't forget that we need to now calculate the stress in the wire. All right, so some of this information, we might need here, but if we just remember, like, stress is the force per area, it's the same thing as pressure, right? Pressure and stress are sort of defined the same way. So here we only care about the wire, right? So the force that we're going to use is the 15 newtons, right? That's the tension in the wire. And the area they're giving us up here. So let's go ahead and clean this up a bit. There we go. And now, remember, what is stress? The joke is, it's what I'm feeling right now as I try to calculate this. 15 newtons over, all right, 3.2 millimeters squared. This squared here means millimeters times millimeters. And so I want to convert millimeters squared to just meters squared. And I'm mindful that there's 1,000 or 10 to the 3 millimeters per meter. You've got to divide by 1,000 twice, or you've got to divide by 1,000,000 in order to convert square millimeters to square meters. So it's going to be 3.2 millimeters squared, and there is 10 to the 6, okay, millimeters squared in 1 meter squared. So until you're really comfortable taking care of that squared or that cube unit this way, just lay it out like this with your calculations. You know, millimeters squared is millimeters times millimeters. You've got to convert each one of them, right? So account for all of that. So 3.2, it's just going to be times 10 to the negative 6, right? So we can, you know, this 10 to the 6 in the denominator. So 3.2 times 10 to the negative 6 meters squared. Newtons per meter squared. There's the PA, pascals of pressure or stress, right? Again, they're defined the same way. All right, does anybody know what 15 divided by 0.000032 is? That's correct. Whoever said 4,687,500. Well done. Let's call it a day. 4.7 by 10 to the 6 pascals. This is Dr. Schleich, still living the physics life, and we're calling it a day. We'll see you next time.